Thank you, Svenja, for the introduction. So, yeah, as mentioned, I will talk about some general level differences between SQUID and OPM measurements of the systems in general in terms of interference suppression. And I will concentrate on this like magnetic field expansions mathematically. That I will explain that in a minute. And related to that, I will also talk about calibration and head movement issues, or especially considering infant measurements, because that's the main expertise of the institute that I represent. We study the cognitive development of infants. And I will then give some kind of like, well, a summary and maybe some kind of recommendations on what we should do specifically in OPM measurements. So when it comes to noise suppression, there are lots of methods that really apply similarly to OPMs and SQUID MEG, like obviously some basic filtering, that kind of things. Many applications of like signal space projection, that kind of methods as well. But the signal space separation method is something that we need to kind of rethink a little bit. It's a quite widely used method, which is based on expansion, like a vector spherical harmonic expansion of the magnetic field. So we have to think about the geometry differences in OPMs and SQUIDs. So I will not have a lot of math here in this talk, but I will start with this. At least it kind of helps me go through what's going on here. So this is the basic idea of the vector spherical harmonic expansion. And this is a very general model. It doesn't really, it's not restricted to MEG in any way, but it is like kind of relevant to this geometry that we have, where we have sensors that are surrounding something that's of interest to us in such a way that they confine this green volume, which is the interesting part of the world, and then we have that red space that extends to infinity. And in between, where we have no sources of magnetic field, that's where the sensors are, the magnetic field can be derived from the magnetic scalar potential, which by definition satisfies Laplace's equation, which has this basic solution with the expansions that converge at infinity or at the origin. And anything that is produced by the brain, like in this internal volume, has to converge to zero at infinity, of course. And that's why that's expressed by the first expansion that decays inversely proportionally to the L+1 power of the distance from the origin. And then we have this other part of the expansion that converges to zero at infinity, at the origin, and that is the part that is the external interference in the red volume. And then the question, so this is like, there's no arguing about this, it's just the basic solution for the magnetic field under the quasi-static approximation. But then the question is, like, where do we truncate these expansions? And that's where we have to have some assumptions about what the systems are capable of measuring in terms of spatial frequencies that Lauri already talked about. So in the SQUID systems, we truncate the first expansion at the order of 8. That's the expansion of L. And then the outside is typically like 3, which corresponds to 15 components. And then in the SQUID system, we have like 95 components. But for the OPMs, now that the sensors can be placed closer to the head, we can think about increasing the expansion order because we can hopefully measure higher spatial frequencies. So I'll talk about that now. And sometimes people are worried about the rank reduction based on this, but it really is the rank that we reduce is just truncating the highest spatial frequencies that are below the sensor noise levels. This is just an illustration of what these magnetic field components in this expansion look like when we go from the lowest spatial frequencies to higher and higher, so they get more and more complex. That's on the left side, the 21st VSH components. On the right side, we have the lead field vector of an of an MEG system, and then we take the signal value decomposition. And similarly, we are looking at the 20 most significant left signal vectors of that expansion, and you can kind of see that they are very similar. So even if you do this as an SVD of the lead fields, you get kind of a similar structure of these spatial frequencies. And now the idea is that for high precision of the MEG measurement, we want to be able to detect as high spatial frequencies as possible. And obviously, if you can place a lot of sensors closer to the head, which is the case with OPMs, you can probably get higher spatial frequencies, and that way better spatial resolution. This is an illustration where we did the minimum norm estimate of a simulated source as a function of spatial frequencies in terms of the VSH expansion. You can see that I'm concentrating on the upper part of this image where we have a kind of a superficial source. You can go up to this spatial dispersion that is illustrated by this color. It keeps improving as you go higher into expansion. Like we go to expansion order of 13, and it keeps improving. So if we can measure with OPMs something like this, like up to the order of 13, we will get better resolution. And now, if the expansion order increases from 8 to 13, the number of components goes up from 95 to 210 degrees of freedom in this model. So instead of like having about 300 squids in the OPM world, we probably want optimally at least something like 500 sensors based on this idea, which seems to be quite well in line with what Lauri was just talking about, using a slightly different approach. So that was the first part of the with OPMs. If they work well, we have lots of sensors. We want to be able to increase the truncation of the VSH model, and that kind of tells us that we can get a better spatial resolution of the inverse model. Another thing is that if we have flexibility in the sensor array design, we showed already like more than 10 years ago that this symmetry breaking is very beneficial. So we actually built this SQUID system. There's only one of these built, but it exists nowadays in Japan, where we lifted some of these sensors, or we added sensors that were like orthogonal to the existing 306 channel SQUID array, and we got much better resolution between the internal and external parts of the magnetic field, and better reconstruction noise. And then later, like last year, we did a simulation study where we used simulated annealing to optimize the condition of the VSH model. Sorry. That was a reminder to take some medication. I was attacked by a magpie 2 days ago, so I have to take some antibiotics now. Yeah, not only snakes and spiders are scary in Australia. Okay, so in the lower image, we did a simulated annealing study where we let sensors optimize their orientations and locations to optimize the stability of the VSH model. And we get this result where it's kind of the orientations are kind of like shuffled in an interesting way. So it really makes sense to break the symmetry of the measurement. But if we don't have a system where we have a lot of sensors and maybe we don't have all that freedom to place them whatever way we want, we can also do numerical kind of tricks. This was a recent study by Niall Holmes and others where we developed this iterative pseudo-inverse for the SSS model, where instead of like taking the pseudo-inverse of the whole matrix to get these components for the internal and external part of the signal, we do it in a way where we exploit the hierarchy of the system, because the lower spatial frequencies carry farther in space and they have more signal energy. So we do the inverse first for those, then we subtract them, and then we go to the higher order and have a very stable matrix there and go on like that. And this really helps a lot. So in this case, it was a 192 channel system. And you can see that when you increase the expansion order of L in, if you just do the direct pseudo inverse, it's very unstable when you have high order expansion orders, and your reconstruction noise, which is the middle column here, the inverse of the SS matrix increases your noise in your estimate a lot. But then if you do this iterative system, you can see that if you have like an order of 10 or something, and you increase the noise initially by a factor of 10, now with this better numerical way of doing it, you actually get a reconstruction noise level, relative level of better than 1. So you actually decrease your noise level a little bit. And then finally, about noise, this kind of noise suppression methodology. One problem that we might have is that when we have the OPM geometry where you put the sensors directly on the head, you might not be able to find a hypothetical sphere. This has nothing to do with any conductivity model or anything, but it's a convergence volume that has to be spherical. You might have a hard time finding an origin for it where you actually cover all of the brain if your sensors are attached to the head. So what we are doing now is, so my student Stan McPherson is working on this, where you do like a two or multi-origin VSH expansion where you have like these overlapping spheres, and then you combine them into one basis which covers the whole brain. Or you also have the option of using other than spherical harmonics. So here we have the spheroidals. This was developed by Tim Tierney and others very recently, where you have a different kind of a convergence volume because you have different mathematical basis functions, and now you have the whole brain covered nicely. Okay, one thing about, an additional thing about this is that if you have artifact sources that are very close to the head, typically we do this spatiotemporal SSS method called TSS, where you can efficiently suppress artifacts that are coming from things like vagal nerve stimulators. The high dynamic range of the squids really helps here because quite typically those artifact sources don't saturate the sensors, and we can efficiently suppress their impact. As far as I know, this is still quite a big problem in OPM measurements, having these kinds of artifact sources, and this is something that has to be dealt with if you have like braces or things like that. Yeah, so that was those were like the main aspects, like differences between how we approach noise suppression with these expansions in case of squids and OPMs and how they are different. And then I wanted to say something about calibration. So obviously we want calibration to be accurate for accurate forward and inverse modeling, but also it's important for SSS processing to have accurate calibration. And also OPM MEG systems, because we may have higher spatial frequencies that we can measure, so we see things more clearly, but then we also see these errors more clearly, like calibration errors and other kinds of errors. So we have to take special attention to those, because if we want to leverage the potential that OPM MEG has, we have to really pay attention to that. So I want to talk a little bit about these different approaches. So we can use a precisely known calibration source, for example, the phantom head. It relies on the fact that we know the source very accurately. Or we can use a known calibration source, which doesn't necessarily have to be so accurately known, such as field compensation coils that we typically have in shielded rooms. And then the third approach, which we use with the 306 channel system, typically is the fine calibration, where we just require compliance of the MEG system with